record. There we go. Okay. I think we've got this. Okay. So today what we're going to do is we're going to get into kind of the nuts and bolts of actual hypothesis testing. Okay. So in real quickly, and we'll probably click through this reasonably quickly, not as fast as we did before, but still a lot of this is going to be almost certainly review of things that you've already been exposed to previously. Talking about distribution of sample means, this is a really, really important concept for getting a good conceptual handle on what we're doing with these statistical tests. We're going to talk about central limit theorem and then our null hypothesis testing. And then here at the end, what we're going to do is we're going to get into criticisms of our testing procedures and some recommendations, okay? Basically, everything we think we're doing, we're not doing, and it's caused problems in our science. And so we're not responsible for fixing these things, but we can be responsible for knowing what our analyses do say, what they don't say, and sort of making sure that we're tailoring our interpretations to be sort of more accurate and representative of the types of things that we can say about our data. A lot of this involves being comfortable with ambiguity, right? Again, as we've talked about before, we like to put things in boxes and say, oh, if it's this, and if that, it's that, and we are 100% certain or 100% not certain about this stuff. In general, it's all kind of up in the air all the time, which makes things difficult, but it makes it incumbent on us as researchers to start looking at strength of evidence, cumulative evidence, convergent evidence for something, as opposed to just putting too much stock in one-off studies. Sometimes one-off studies can be really good and really suggestive, but again, trying to temper the conclusions we make from our own research, other people's research, even if we would prefer not to. So to this point, what we've done with our z-scores and things along those lines is we've generally looked at the location of probability of some score within a population of scores, right? So we say, here is the distribution of IQ scores, right? What's the likelihood of finding someone who has a score at this level or above, or between these 2 points, or something along those lines, right? Which is a cool trick, right? But generally, what we're doing in our applied research is we're rarely interested in one person's score, right? That's generally not what we're running studies to do, right? What we want to do is we want to make inferences, oftentimes with group-based analyses, on the means that we're saying. Okay, so I've got this sample. Here's the mean of this sample. What does this tell me about some phenomena that I'm looking for or sort of trying to study, right? So the nice thing about the stuff that we've done kind of lays a foundation, because just like we are able to go through and in a distribution of, let's say, IQ scores, Teresa, I can ask you, hey, how likely it is for someone to have a score of 130 or above? And you can say, well, based on the population of scores, we know a normal distribution. We can say that sort of this is the percentage of scores that would likely to befall, or this is the likelihood of us grabbing one random person who falls above this, right? What we can do is we can extend the same process out, and we can start drawing inferences about the representativeness and likelihood of extracting a sample of a given size and a given mean based on sort of known qualities of sort of that distribution where we're going to be pulling that sample from. Okay, so all the same things that we did with the single scores, being able to sort of assign probability statements to, we can go through, take that same process and extend it out to start making probability statements about the likelihood of obtaining some mean of a certain size with given characteristics assuming some things, or given that we assume some things to be true, okay? So basically what we're doing is we're saying, given all possible sample means that could be pulled from this population, what's the likelihood that we would obtain something having these characteristics or something more extreme? Okay. And the way we do this, and so the way how we're needing to sort of level up with sort of conceptually what we're doing, is we need to start working with our distribution of sample means, okay? This is kind of this gets a little bit heady into statistical theory, right? But what we're talking about with our distribution of sample means is if we took a distribution and the individual individual values in that distribution were means obtained from all possible samples of a particular size that could be pulled from a population, technically with replacement, that's going to give us our distribution of sample means. So before we have a distribution, right? We like our distribution. That's easy to think about, where we say, okay, here's my distribution. And before we were talking about, this is the distribution of height in the US, where individual values in here are individual people. With the distribution of sample means, same distribution, right? But instead of individual scores, these are individual samples, okay? So let's say I have sample equal to 50, right? If I were to go through and take all possible samples of size 50 from the US population, if I had the capacity to do that, randomly went through and selected 50 people across the country, measured their height, took the mean of those 50 individuals, and had that to be my data point, these are the individual values in this distribution here, okay? So our observations now, instead of being individuals, our observations are sample means, okay? And so our unit of measurement is sample means. People, questions about sort of what we're doing here? Yeah.
So if you say samples of a particular size, I was wondering if you could use different sample sizes if you weighted each of the sample sizes to construct this distribution.
Okay, so this is the thing. In this, so of this sample size, of this size, okay? So if I start changing the size of my sample, I'm talking about a different distribution, changes it completely. So in this distribution, these are all samples of exactly 50, okay? So it's not, so some of them are going to be like, oh, like I got a sample of 49 here and 64 here and then 100 here and 10 here. Nope. Mathematically, theoretically, we're saying specifically of sample size 50, because Matt, what happens is we start to increase or decrease the size of our sample. It starts to change the shape of that distribution. Okay. Good question. Other questions? Okay, so this isn't a real thing. This isn't something that we, in practice, except for maybe a very, 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 very rare situation, are ever able to do. This is a theoretical, conceptual thing, right? Sort of like our population parameters. Never will I know the exact value of the average height of adults in the US. It's a number that's out there. Conceivably, it could be calculated given infinite time and resources, but it's nothing that we'll ever actually know, right? Same thing, distribution of sample means we'll never actually observe that, because there's no way I could go out and randomly select with replacement all possible samples of 50 from the population. But luckily, what we can do with a little bit of math is we can go through and start to figure out sort of what the distribution, or what this distribution should like, and what the characteristics could be or should be. So functionally, countless number of, I don't know sort of what that number would be, given the population in the US, how many samples with replacement of size 50 that could be drawn from the population. Functionally, it's countless, right? It's functionally infinity. It's not, it's an actual number, but it's more than we can sort of work with. And it's impossible to go through and do this all in person, but luckily what we have is mathematics. So people smarter than me have gone through and figured out the theoretical properties of these distributions, okay? But let's start with an example, okay? Something where we can actually go through and create a sampling distribution. Let's say we have some population of 4 units, or people or animals or something like that. These 4 are the only 4 in the universe. This is our entire world right here, okay? Now, if this was our entire world, do we need to run statistics with this? No, we just ask like sort of what are the scores, and those are the scores, right? Is this score higher than that score? Yeah, because it is, right? We're working with population-based parameters. But for the first purpose of illustration, let's say we have a population with score 2, 4, 6, and 8, nice even numbers. The mean is 5. Okay. Sam, how would you describe this, the shape of this distribution? Yeah, this is a
Like, if we literally draw a curve over the frequency, literally draw a curve over those bars.
Yep, exactly. Yep. We could call this a flat distribution, a square distribution, a uniform distribution. I've got 4 scores, all with different values. Is this, Sam, is this a normal distribution? No, not even close, right? But what we've got is we've got individual scores and we've got the mean, okay? Now what we could do is we can, with this population of 4 scores, we can go through and we can physically create a sampling distribution of this population, and let's say for size of sample 2, okay? So we've got a low number of people. So we're saying if we go through with those 4 observations, we can pretty quickly plot out all possible samples of size n equals 2. So with 4 scores, what we end up is 16 unique possible combinations or possible samples of size 2 here, right? So here, our first sample, we just grabbed the first person, and then we grabbed the second person again because we're doing it with replacement. So here's our first sample, second sample, third, fourth. These are all the possible combinations of 2 in this group of 4 that you could get, okay? And so what this does is this creates my sampling distribution. And if I won't go through and I calculate the mean of all possible samples of size 2, what I do is I get the mean of all those 2 unit samples that could be collected with replacement from this distribution, okay? People see what we did here? And again, it's a very, okay, not quite clear. Thank you. No, sometimes people don't. Okay, so what we did here is we've got these 4 cases, okay? What we did is we just went through and we said, okay, we want samples of size 2. But we can do it with replacement. So I've got 4 scores here, right? And so in my first possible sample, I go through and I pull the person who has a value of 2 and I put them back and then I get them again, okay? So that's one sample of size. The second possibility, I pull 2, put it back, and then I pull 4. This is these scores.
Oh, right. Okay.
Okay.
Yes.
Yeah.
Sorry.
Yeah. No. So this is what we're doing, right? And so these are the values of the individuals that we're pulling. Okay. Did that
Yes,
click that?
makes sense.
Okay. Yeah.
So you're saying with replacement, you just have repeated values.
Yep.
Another frequency is.
Yep. Exactly.
So,
Okay. Yeah. And when we're working with, this is not something we want to do in our actual research, but for statistical theory, this sampling with replacement starts to be an important concept, and it's something that is kind of at the foundation of this stuff. When we're actually sampling for statistics, we don't want to do that because then you get problems with dependency. But for theoretical purposes, this is what we're doing. Yeah, Elizabeth.
Well, I think you answered my question now, but it was going to be why are we able to replace, because normally number one. So you're saying hypothetically we're able to replace right now?
Yep.
Otherwise it's going to be-
In order for the theory or for the underlying theory, it's always sampling with replacement. And this is what we'll see too when we we won't do much with this, but later on, if you get into bootstrapping samples and things like that, it's always sampling with replacement. Because otherwise, if I have a sample of 100 and I want to create a bootstrap sample of size 100, if I didn't have replacement, I just have my sample again and again and again, it would always be the same, right? So sampling with replacement is, if we're doing these more stat theory types of things, is generally the assumption. Yeah.
So, well, like, what is like the reasoning behind selecting a sample size?
Okay, hold on to that. We'll get there. Okay. So in this scenario, just four individuals, 4 values, right? square distribution. And what we've done is created a sampling distribution of sample size 2, which gives us a total possible combinations of 16. Like those are all the samples that could be drawn that are unique here. And so we go through and we calculate the means of each one of those samples. And something then interesting happens if we go through now and create a distribution of those means from all possible samples of size 2. What we get is the sampling distribution, okay? What we have here is the sampling distribution for this population of 4. All possible sample, if we take the mean of all possible samples of size 2 and we go through and plot those out, Basha, what happened here? What does this look like? It looks like a normal distribution, right? What is, where do we find the most values? At 5, right? And things start to slowly taper off. What's the highest score that we can get? The highest score?
Oh, I'm sorry,
8. And the lowest score?
2.
Right. And everything follows into this nice distribution right here, right? How does this compare to our original distribution? Yeah.
Is there any implication with like the mean is 5 and this one, and that's not reflected by like an actual value?
That's a good question. Again, we're using these. This isn't a continuous scale, okay? And so, yes, in terms of this getting back to levels of measurement, right? For this, 5 is the mean, but 5 is not an actual value that's observed in this. But if
Yes, but then it makes sense that it would happen when you do the sample means.
right.
And it would be your best guess.
Right.
for what-
So, and this is what we see, right, is because right here, the mean of our population mean is 5. What is the mean of the sampling distribution here? 5, right?
Yeah.
And so what we end up with, this is a very, very simple example, right? And some cool stuff happens when we've got just 4 scores, sample sizes of 2, makes it possible to go through and explicitly identify all possible samples of size 2 that could be drawn. We take the mean of those and then create a sampling distribution, and we get this nice normal curve. It's uniform, it's predictable. The nice thing is, and the whole thing that makes statistics work is this happens no matter, or well, not no matter, but this is a general rule that these sampling distributions follow, okay? Characteristics of our sampling distribution, the sample means will pile up around the population mean, okay? And eventually what we get is a mean of the sample means, or like the expected value of the mean is going to be equal to the population mean. So by definition, the mean of our distribution of sample means is going to be equal to population mean. Josiah, can I ever actually know the population mean? No, I can't. But if I have reasonably sized samples that are representative, and I go through and sort of run that over and over and over and over again, theoretically, I should start to, the mean of that distribution is going to be equal to my population mean. So then I can know the population mean or something very, very close to it, sort of given my statistical methods, okay? Now, does that mean all possible samples are going to be equal to the population mean? Nope. Some of my samples are going to be out here. Some of my samples are going to be out here, right? But on average, the mean of the sample means is going to equal the population mean, okay? Our distribution of sample means is generally going to form a normal distribution, all right? Yeah.
How do you know like how many studies you need to assume that you're getting at the population needs?
Well, we're all working with theoretical concepts right here. In actual practice, it starts to get more complicated because then we have variability in methods and measures and how things were gone through and conducted and things along those lines. So these are still sort of in theory types of things. When we get into some meta-analyses and things like that, that starts to help out. But this is still not something that, because again, we can't collect all possible sample means of size, whatever. So we're still working in some mathematical theory with this or statistical theory. But what we can do is use this to start to infer things about the likelihood of results and things like that. Okay. But Katie, when we're thinking about distribution of sample means, generally form a normal distribution. Is this a normal distribution? No, but this is my sampling distribution is, right? And so the same thing, if I look at sort of marijuana use in college students, is that a normal distribution?
What do you mean? Like,
Like sort of frequency of use of marijuana in say college freshmen. Is that something that's a normal distribution?
it can't be.
Well, we're talking about like all college students. Does marijuana use form a nice natural distribution if we're thinking about sort of ounces of marijuana smoked in a month? Okay, no, it's going to be skewed, right? But if I go through and I'm even though my population distribution is skewed and not normal, distribution of my sample means should approach normality as my sample size starts to increase, right? And that happens actually fairly quickly. So even though we're working with something some phenomenon that's out there in the universe that doesn't have a normal distribution, my distribution of sample means will start to approach normality pretty quickly if I have sort of good methods, okay? And what we can do, and the nice thing that we can work with here is that we can use this distribution of sample means, just like we use our Z-table, to go through and start to answer questions about the probability of selecting a random sample with a given mean, okay? So even though sort of this is kind of what we started with, we're working with something now that's much more uniform and predictable based on some statistical theory. Yeah, Elizabeth? No.
So the graph on the left,
Uh-huh.
going to the graph on the right.
Uh-huh.
The determinant factors showing us or helping us get to the graph on the right, is that just by increasing your sample population along with just repeating measures? Or are there other factors that are really contributing in order for us to be able to get to the graph shown on the right?
Yeah. No, those are all good questions. And this is why I've got this hash. You say, usually it will sort of end up doing this. Now, we have all sorts of underlying assumptions about representativeness of our samples and that we're have accurate measurements and that our samples are sufficiently large, things along those lines. As those start to break down, then this starts to get questionable. But in theory, if we've gone through and done all those things, then this is what's going to happen in terms of our sampling distribution. And we'll get into, in just a few slides, some of the things that start to influence that. Okay.
I guess, sorry to
Yeah.
clarify from my mindset, so the main factors are gonna be a larger sample size. Replications. Or
Well,
are those not even gonna really influence it, it just happens now?
it'll happen naturally. It'll happen naturally. Okay. Because again, this isn't dependent on the number of replications necessarily, because this constitutes all possible samples of size n. So it's not like, oh, if I do this 20 times or 30 times. Now in practice, yeah, as you start to sample more and more and more, it'll start to approach this more and more quickly. And I've got a pretty cool video where I'm actually doing this. I'm going to strongly recommend you to go through. This is basically me generating random sets in SPSS and doing exactly this with actual bigger data. And it's shocking just with random data how fast this starts to work out. So the number of replications in theory isn't a thing because it's predicated on all possible of size, sample size, sort of whatever. But the size of that sample starts to change the shape of that distribution, or not the shape, but the variability in that distribution. Okay. All good questions. Yeah, Kitty.
So if you like just can't get like a normal distribution, normally is that just like a reflection of your methods? Like,
No.
what do you mean?
No, because if I go through, if I take a look at these samples, are any of these samples normal? Nope, none of them are, right? And so this is a thing. so this is great. These are all fantastic questions, and I'm glad you could, because what we're going to end up talking about three distributions. We've got a population distribution, we've got a sample distribution, and then we have the distribution of sample means. All of those are going to have different characteristics, and as we walk through, you'll start to see how those lay out. Okay. All right. So characteristics are sampling distribution. We have sample means pile up around the population mean. Okay. Distribution of sample means is generally going to form a normal distribution, right? And again, remember, this normal distribution isn't the distribution of any one given sample, but it's this distribution of the mean of possible samples. And then what we can do is use this for some statistical calculations. So again, if I go through and I take a look at this right here, Sam, what's the probability of selecting a sample having a mean greater than 7? 1 out of 16. So I can tell you exactly, with a population of 4 scores, I can tell you the very specific probability of randomly selecting a sample of 2 with replacement that's going to give you a mean that's greater than 7. There's one way to do that out of all possible things. So what we have done here is, even in this very quick example, we've started to assign likelihoods. If sort of this is sort of my population, the likelihood of grabbing a sample with a certain characteristic given these assumed parameters of our population. Okay. So if we're using not populations of 4, we're using populations of populations, right? What we can start to do is fall back on some mathematical theory to start understanding exactly how this stuff is going to fall out. A lot of this falls on simple limit theorem. Okay. Here, we're saying that for any population with a mean value of mu and a standard deviation of sigma, the distribution of sample means given a sample size n will eventually end up with a mean that's equal to the population mean, and a standard deviation of that sampling distribution that's equal to the standard deviation of the sample, or standard deviation of the population divided by the square root of my sample size. And it will reach a normal distribution as that sample size starts to approach infinity. Okay. So what central limit theorem is saying is that if I have a population with a certain mean and standard deviation, doesn't matter what the distribution of that sample of that population looks like. Population could look like anything, right? But it's got mean mu, standard deviation sigma. Distribution of sample means for a given sample size n, let's say 10. If I go through and collect all possible samples of size 10 with replacement from that population, eventually what I'll get is a distribution of means where the mean of that distribution is equal to the population mean, and the standard deviation of that distribution is equal to the population standard deviation divided by the square root of my sample size. Okay. And it's going to approach a normal distribution more quickly as my sample size starts to get bigger and bigger. Okay. So Katie, to your question, if I'm collecting sample size of 10 or sample size of 100, that distribution of sample means is going to approach normality much more quickly with sample size of 100 versus sample size of 10. Okay. Oh, yeah. What's that, Sam?
I was gonna ask. But I think I might, sorry.
To ask if there's that
Yeah. That's getting into sort of more statistical theory than sort of I sort of can peel off the top of my head. That, I don't know, that's magic. So I'm not sure exactly why this happens, but it is something that we see is a characteristic or a property of this sampling distribution. Okay. So what we get in terms of thinking about our distribution of sampling means the shape. Okay. Distribution of sampling means you get to approach a normal curve if one of 2 conditions are present. One, the population from which the samples are drawn is normal. Okay, so if I have, let's say, for example, that conscientiousness, okay, personality characteristics. Let's say conscientiousness has a normal distribution in the population. I don't know if it does. Seems reasonable. sort of this natural bell curve. If I'm going through and grabbing samples and measuring conscientiousness, because the population of scores from which I'm drawing is normal, then my distribution of sample means is going to start to become normal very quickly. Okay. But even if I'm drawing from some phenomena that does not have a normal distribution of scores. So Sam, let's say number of binge episodes per year. That's probably not a normal distribution of sort of some phenomenon, right? In the population. Yeah. Okay. Probably not. But if I go through and I'm collecting sample sizes of 30 or more, the distribution of sample means still starts to become normal very quickly, even though the thing that I'm measuring is not normal. The distribution of the sample means, the mean of the sample means that I'm plotting out, that's going to become normal very quickly, even if sort of what I'm measuring has kind of a crazy skew on it. Yeah, Katie.
Okay, so I have this in my head, but I don't know if it's gonna come out.
Yeah.
Correctly. But for this, does it matter like the prevalence of something? So if it's like a super rare disease with like it only affects like 1% of the population, like is that something?
Okay. So you get a little bit of a tweak here. So what we're looking at is the mean value of something as opposed to like the prevalence or the rate or something along those lines. So not the yes, no occurrence. That's going to be a different distribution.
But finding like a normal distribution, because like I get what you were saying for the binge episodes, like once you get a sample of around 30 or more, then it like it'll start to become like normally just like distributed. But for like if it's like something really, really rare, is that still the case where if you get a sample and like if you get a sample of like 30 or more, or no, because of the prevalence rate of
Oh, no, it still will. So, I mean, think about, if we think about, and again, remembering that we're measuring the average or the mean of something in a sample, right? So I think even sort of binge eating is nice. So if we go through and we take a look, and the majority of people, well, I don't know. Depends on, this isn't my area, so I'm just kind of making things up. But probably you're going to have a small proportion of people, you're going to have people who overeat on occasion, right? And so those are going to be stacked up on this end of the distribution. And then you're going to have people with diagnosable eating pathology that start to bring that tail out to the end, right? Now, if I go through and I just have random samples of size 30, where am I probably going to capture most of those folks?
or not.
Yeah, so we're going to catch this part of the distribution, right? So if this is my distribution of my stuff, right? And my sample mean is probably somewhere right there, right? If I have random sample sizes of size 30, where are most of my scores going to come from? In this distribution.
Yeah. Oh, I like where the mean is.
Yeah, so they're probably right here where the bulk of things are. Most of my scores are going to come from here, right? And so is the mean of sort of the stuff that's going to come over here, is that going to overestimate or underestimate the population mean? If I'm pulling scores and most of my scores are coming from here, on average, are scores just pulled from here? Are those going to overestimate or underestimate my population mean? Want to give her a hand? Yeah. Underestimate, yeah, because most of my scores are coming from here, right? And this is an underestimate of my population mean, right? But every once in a while, I'm going to get stuff that's coming up here. And every once in a while, it doesn't happen very often, I'm going to get stuff that's coming out here, right? And so when I go through and I plot out the distribution of sample means of, let's say, n equals 50 here, what I'm going to find is that the mean of my distribution is going to be equal to the population, right? And what I'm going to find is that a lot of those scores are going to be down here, getting sort of lower because they're kind of pulling from this. But then I'm going to get some samples that are going to pull me higher because they're pulling out here. And so what we get, even though we're working with a distribution that's very skewed, and even if we go through and look at something, yeah, even a more rare case or something like that would still be the same thing, right? But what we find is that the mean of all possible samples of size 50 are still going to follow this nice bell-shaped curve. We're going to have some that are higher, some that are lower, but most of them are going to center right here in the middle where the actual mean of my population is. Now we can have a discussion about whether the mean of the population is kind of what we want to get at because it's skewed and it's going to pull it out. But what we're finding is that the mean of my, the expected value of the mean of my sampling distribution is going to be equal to population mean here. This help kind of,
Yeah,
okay, Amanda?
okay, just to clarify on that, so that first distribution, like you're looking at one sample, so those are all individuals,
Yeah, this is my population. This is individual scores.
right? And then when you get to the second one, that now all those individuals just become one sample. in all.
Okay, nope, this is, yes, close. So this is mean of n equals 50, right? So here, we're talking about individual people. Down here, we're talking about means. Okay, so this is an average score of sample size 50. This is our just our population where this is the distribution of individual scores. Okay, so this is a sample that is tracking scores for all individuals, all people. If we're talking about people, all people in the population. This is a distribution where my mean or where my unit here are average scores or mean values for sample size 50. So here, my unit is people. Here, my unit is sample size 50.
But that's not, the one above, not necessarily 50 people as well, that's all people.
What's that? Yeah, this is all people. This is
Okay.
this is all members of the population. Yeah.
That's what I was just getting lost with. The top graph
Uh-huh.
represents the population that's not an N of 50. We chose an N of 50.
Yep.
Okay.
Yep. We can make this 10. We could make it 100. We can make it sort of whatever we wanted to make it.
The
Yeah.
top was not representing a sample.
Nope. That's just individuals. That's just sort of what things look like out in nature. Yeah. Just that.
How would you pick your numbers for your sample?
Okay. That's a good. We'll hold on to that. So we'll go through and talk about this. Okay. So what we're talking about here in terms of the shape, what we see is under, and this starts to become important. And when we start to look at our means-based tests and think about our underlying assumptions, right? Our underlying assumptions are actually about not the scores that you're observing, they're about the distribution of sample means, okay? And so this is why it starts to become important to recognize that even if I have something that's funky looking out there in the universe, I can expect my distribution of sample means to start to become normal pretty quickly. Either one, if the population of that I'm drawing from has normal value, or the distribution in the population is normal, or if I've got sample sizes of about 30 or larger. If either one of those two things are met, what we can assume is that the distribution of sample means for whatever we're measuring is going to be relatively normal and symmetrical. Okay, I got that. Yeah. Yep. 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 So even if, and sort of thankfully, right, because a lot of the stuff, particularly as clinical people, a lot of the stuff we're measuring is not normal, not even close, right? But if we have good methods, what we can assume is that the distribution of sample means, which statistically is what we're interested in, that will start to reach normality if either one of those two things are taking place. Okay. So this is the shape of our distribution. Distribution of sample means we can also we know things about the measure of central tendency. So the mean of the distribution of sample means, right, or the average of all possible sample means of a given sample size is going to be equal to the population mean. Okay, so and we call this sometimes it's referred to as the expected value of the mean. Expected value of the mean. This is just the mean of the distribution of sample means, and it's equal to the population mean. Okay, so here we have we're looking at, let's say, adult height, right? And in the population, we say that adult height, the average adult height in the U.S. is 68 inches. I don't know if that's true, but so let's say that it is, right? if we were to go through and select all possible random samples of adults of sample size 100, if we were to go through that and then take the means of all the infinite, or so let's say 10 billion, it's way more than that, but 100 billion, like say it's 100 billion samples. There's 100 billion possible samples of sample size 100 that could be drawn from the US population. If we went through and took the means of all those samples 100 and plotted those out, we would get a normal distribution, and the mean of that distribution would be 68 inches. It'd be identical to the population mean. Okay. So this expected value of the mean is where we can start to, at least from a mathematical standpoint, we can start to know what the population mean is, even when we can't observe it correctly. Questions about central tendency? Okay. And here's where we start to get into sample size issues, okay? The variability of this distribution, okay? What we know, and so we know what the shape is gonna look like, and we know what the mean is gonna be, but where we start to see an impact of some of our decisions in terms of sampling is in the variability of this distribution, okay? The standard error of the mean, or the standard error, okay? This is just the standard deviation of the distribution of sample means for a sample of for samples of size. Okay, so if we go through and we take a look at my distribution of sample means here of all possible random samples with replacement of adult height with sample size 100, my standard error is just the standard deviation of this distribution. Okay. And I calculate my standard error by taking the standard deviation of the population, divide that by the square root of my sample size. That gives me the standard deviation of my sampling distribution. Standard deviation of the sampling distribution is just going to be what we see listed as our standard error. Okay. All this is just a standard deviation of your sampling distribution. Okay. So all the same interpretations we applied previously in like that first lecture about standard deviation, it's the same thing except you substitute sampling distribution for sample of scores or population of scores, right? So the standard deviation here of my sampling distribution, I can interpret this as an index of how much difference is expected from one sample to the next. Because remember, my units in this distribution are samples, right? This is all possible samples of size 100 that could be extracted from the population, right? And if I go through and plot those means out, the standard deviation of that distribution is just telling me how much difference I should expect from one sample to the next, right? On average, I can expect sort of this sample to vary about or differ from about this other sample from this number of units, right? Alternatively, I can think about this as an index of how well an individual sample mean estimates the population. We're talking about error here, right? So if we're thinking about just our sample, we're thinking about just a sample of scores, right? And I say, oh, hey, what is the standard deviation? You can say, oh, the standard deviation is about how much difference we would expect between any two randomly selected samples. We talk about it as the expected difference between any randomly selected sample and the mean of the sample. Well, we can apply that same here. If this is the mean of my sampling distribution, my standard error is telling me how far any randomly selected sample from this possible distribution is going to fall from my actual population mean. Okay. Now, if what I'm interested in is estimating, getting a good estimate of this population mean, do I want larger standard errors or smaller standard errors? Smaller, right? Because it's saying, I'm saying, hey, my sample, Basha, you have a sample in your hand. Hold up your sample. This is your sample, okay? And it's sample size 100. So it's a pretty good sample, we'll say, for the types of stuff that we do. And I say, Basha, is the mean of that sample identical to the population mean? What are you going to say? Probably not, right? But if I ask you how close or how confident you are that that was a good estimate of the population mean, you probably want to look at your standard error, right? And say, okay, well, you know, if my standard error is probably small, I'm saying, yeah, it's not perfect, but it's probably pretty close. You know for sure if it's pretty close? Yeah, well, and you've just got one sample, so you can't calculate it, so you don't know, right? It's possible that your sample is hanging out here. Like that's like there's probably not, but maybe, right? Because stuff hanging out here isn't common. but it happens, right? But based on the information that you have at hand, calculating your standard error, you're like, I don't know. On average, I would think that my sample should be about a little over a half an inch off of what the actual population mean is. Again, I don't know that, but that would be my best guess based on this distribution. You're probably more closer up if you've got good methods and good representative sampling technique. You're probably around here. You could be out here, probably not. You're probably right here, but this is our best guess. And knowing whether you're out here or more towards the center, this is where sort of understanding your content area, understanding what's reasonable, understanding sort of being familiar with previous research. Because if most people are falling in here and you're way out here, then maybe I start to suspect that I might have gotten a bum sample. Not because of anything I did necessarily, maybe it's because something you did, but sometimes this stuff is just gonna happen, okay? As a preview into why our methods are questionable, what happens though if I find something that falls way out here? What often happens? Yeah, we get super excited about it and we publish it, right? Josiah, why is that bad?
Because it's biased on something that could just be here.
Yep. And through no fault of your own, right? Like you just published something that was pretty cool that you found. But if people keep trying to replicate and no one can, there's a possibility because you just got a weird sample that had kind of a weird thing that you could tell a cool story about, but everybody else who's trying to replicate it is right here closer to where the population thing is. And so this starts to cause some problems. Matt, you've been waiting patiently. What's going on?
I was going to ask earlier, but I think it's been answered. So basically, the standard error is kind of an estimate of sampling error between population and samples.
Yeah, it's kind of like, I mean, keep sampling error different than standard. Keep sampling error different than standard error because they're different things. But I think that's a fair way to start to think about this. Yeah. Okay. Yeah, Sam.
I was gonna say maybe that's a helpful way to think about why standard error
Yeah.
like that difference between the
Yeah.
estimate and population transfer.
Yeah.
It's like what you would expect.
Yep, exactly. So, and it just kind of depends. What I want you to do is, and so other thing we can say indicates the expected difference between the sample mean and the population mean. You know, so all these, there are different ways to kind of sort of frame this and contextualize it, and sort of different ways depending on what you're trying to do might make a little bit more sense, right? So if I'm thinking about how well does my sample likely represent the actual population parameter, something like this starts to become useful, right? But if I'm trying to run a power analysis or something along those lines, or if I'm running a multi-study sample and I find a mean value of 20 in this sample, and I'm going to run through and run a replication, am I expecting my next sample to be exactly 20? No, I shouldn't, right? What I should be looking at is that standard error. That standard error is going to tell me on average how much I can expect this replication sample if I do the exact same thing to be, right? And sometimes that may sort of make you happy. Sometimes it may give you heartburn, which is difficult to deal with negative emotions sometimes. But as long as I understand what's going on, I can better plan and sort of interpret my stuff here. Okay. People kind of understanding kind of what this sampling distribution is, how it works, and some of these characteristics. Okay. All right. So factors influencing my standard error. Okay. One thing, population standard deviation. Again, and this is why, like, just look at the equation here, right? It's this value over that value. It's a simple ratio, right? So what impacts standard error? My population standard deviation. As Teresa, as my population standard deviation increases, what's going to happen to my all other things held constant? What's going to happen to my standard error? It will also increase, right? So wanting to know that if I'm measuring something with a lot of variability in the population versus something with little variability in the population, I'm probably going to get more standard error with the thing trying to measure the thing that's got a great deal of variability in the population than something that has very little variability. Okay, but Teresa, are we in control? Do we get to say what the population variability is? Yeah, I wish too, right? Sometimes we can, and this is where measurement stuff starts to come in. If we've got good measures that are reliable measures and consistent measures, that actually does start to, because our objective representation of that thing that we're measuring starts to get more consistent if we've got good positive measures. And so always having good reliable measures is beneficial. And this is where our methodology starts to dovetail in with our stats. Okay. But generally, we don't control this piece of it. What we do control is our sample size to some extent, right? Law of large numbers says the larger the sample, the more likely it is the sample mean is going to be closer to the population mean. You all provided some excellent answers for this in this first problem set, talking about why larger samples decrease sampling error. Same thing here, right? If I've got larger samples, I'm capturing more of my intended population incrementally. I'm going to have more opportunities to capture some of those folks out in the fringe. And so what I'm going to do is I'm going to have less standard, or sort of my standard error is going to shrink. One, because of math, because it's in the denominator, but two, conceptually, this is why, because I'm getting sort of samples that are should be, with good methods, getting closer and closer to getting sort of representing the thing that I'm trying to get at. Okay. Now for standard error, I talked about previously about diminishing gains with your sample size. I mean, if I just take this function and plot it out, like this is what this curve looks like. So for very, very small samples, as I start to add one extra person, I start to get a series of gains in my standard error. It kind of starts to level out here as I continue on. But in general, large samples, always better than small samples in terms of being sort of pushing that standard error down. And we're not there yet, but anybody guess where this standard error value goes in my test statistic, like a T statistic or something along those lines? The numerator or the denominator? Goes in the denominator. And if I have a smaller denominator, what does that do to my test statistic? Makes it go up, right? And if I have larger test statistics, that's going to be generally interpreted as giving me more evidence for more evidence against my null hypotheses than a smaller test statistic. So again, I think this concept of ratios is very important for understanding statistics and recognizing what happens if this happens versus that happens, right? So my sample size goes up, that's in the denominator, my standard error. Denominator gets bigger, pushes down my output, makes that smaller and smaller and smaller. But my standard error is giving me the expected value jumping from one sample to the next, or how well or how off I can expect my individual sample to be from the population parameter. As that gets lower and lower and lower, my test statistic is going to get higher and higher and higher, recognizing that we do have some diminishing gains. But if we go through and take a look at this graph, right, one of the things that you'll see or hear is, oh, you need a sample size of 30 or more, or something like that, or a sample size of 30 is equal to a large sample, right? This is where that's coming from, because when we hit that, that's kind of at the bend or where things kind of start to taper off a little bit. And so a sample size of 30 is not large, it's quite small. But in terms of thinking about our standard error, when we talk about in means-based stuff, large cell sizes, that's generally where this is coming from. Okay. Questions about this? Yeah. Yeah, and that's true of all of it, right? And we're going to talk about why we systematically ignore that piece of things, but it's a foundational component of statistics. Like everything we do is predicated on the assumption of a random sample. Do we ever have a random sample? Okay, so another reason when we start talking about the underlying assumptions of the model, we always violate it, right? And now there's not anything that we can necessarily do about that, right? if the option is to have random samples or not do research, I would work with non-random samples. But what we need to do is recognize the vulnerabilities that that puts and sort of that how that starts to erode our confidence in these statistical models that are kind of built in a vacuum. In theory, if this happens, this is what should result. We're rarely working with that, which means we need to maybe temper our conclusions a bit. Questions? All right. So distribution of sample means here. Okay. So what I've got is just kind of a set of distributions. So here on the solid curve, this is our population. Okay. This is kind of what's going on. But then what I have here are different sampling distributions of different sample sizes. Okay. Which one of these, Amanda, do you think is associated with the smallest sample?
Of the color.
Yeah. Given what we know about characteristics of the distribution of sample means. Okay, so is this, so we're talking about the blue one here. Does that blue one correspond to the largest sample size or in the sampling distribution? Yeah, so which one?
So red.
Red is associated. And how and why can we assume confidently that red is the sampling distribution associated with the lowest sample size? What's that?
This is lower frequency, like
Okay, well, let's focus so yeah, the height is different, right? So it's the same amount of, we'll call it the same amount of scores. What's a characteristic of this red distribution here? How does it compare to the green and the blue? Yeah, it's more variable, right? And so with this sampling distribution, let's say call this sample size 20, right? Of sample size 20, is my mean different than my other two distributions? No, mean's not different, but the variability of my sampling distribution is greater, okay? And what do I call the variability of my sampling distribution? What do I call the variability of my sampling distribution? Standard error, yeah. So yes, the standard error, standard deviation of my sampling distribution is going to be my standard error. But what I've got here is with a lower sample, right? I'm going to get more variability. I'm still going to the distribution of my sample mean or my expected value of the mean is still going to be equal to the population mean, but the variability of those samples, of those sample means, is going to get larger. Yeah.
I'm sorry, but I like still don't understand how you know it's the red one.
Okay. Yeah, Elizabeth.
Oh, well, oh.
Yeah, go.
I can try to answer.
Yeah, do that. Yeah.
and I'll ask my other
Okay.
question.
That's your tax for actually. You have to answer one to ask one.
So on the previous slide, they were saying that like the smaller sample we have, the more error we're gonna have.
Yeah.
So with that being the case, with the tails coming up longer and kind of the red curve being wider, that's denoting that we have more error compared to the blue one, that means it's not as much error. So with us knowing that the smaller sample size has the greatest error, then we look at the red one because that shows it's a more error because it's wider. So that relates to being like the small sample size.
Why is it not the black one now?
Oh,
That's
the
where
black one. I'm sorry. The black one. This is your actual population scores.
Oh, I get it now.
Okay.
I was looking at the black one because I understood the concept and like the variability. and
Okay.
stuff, but I didn't understand why it was the black.
Yep.
Okay.
The bolded line. That's just your actual scores. That's the whole population. The dashed ones. These are your distribution of sample means
Okay,
there.
I get it now.
Okay. Go to Elizabeth
But
first.
let me
Yeah.
ask a question. Kind of what Amanda was saying. Initially, I looked at the frequency and I knew that smaller sample size was probably going to have a lower frequency. So that's how I first finished off it. But then you said, don't necessarily look at the frequency because of the sample error. But I'm wondering, moving forward, are we able to look at the frequency?
Frequency doesn't matter. Frequency doesn't matter. But if we think about what's going on here, right? if I have a larger sample, where those larger samples more likely going to fall? They're going to be tucked closer to the mean. And so I'm going to have more values that are closer to here, as opposed to if I have a smaller sample in this distribution, the sample means they're going to be kind of more spread out. So don't focus too much on sort of the height of these, but it is a reasonable, I want you to be focusing on the variability more than the height, but the height does make sense in terms of how it plays in.
Ignore the y-axis,
Uh-huh.
let's not say, we're just gonna look at the shape, and as far as the shape, the wider it is, means it has more back down.
Yeah. And these are all still normal curves technically. They're just having sort of slightly different, if we were to zoom in or zoom out, then we would get differences there. Yeah.
So when Elizabeth said that, so why there's more error, is that because you have it, and so it's that whole thing with probability of like kill someone?
Well, it's these tails stretch out into infinity, right? So it's not so much that you're going to have more people on the very ends. It's just that you're going to get more variability in those sample means, right? If we think about, I want to estimate, or I want to look at average height of students on campus, right? If I have sample size of 10, the mean of those samples are going to bounce around quite a bit, right? Sometimes I'm going to get large samples, sometimes I'm going to get large values, sometimes I'm going to get small values. If with the sample size of 10, I happen to get a basketball player, that's going to drag that mean for that sample way out. If I get someone who's very small, it's going to drag it the other way, right? So I've got, with sample size 10, my estimates are going to be less stable and they're going to bounce all over the place. On average, they're still going to equal the population mean, but they're going to bounce around a lot more.
We're thinking like more outliers, more errors, that's not.
We kind of got this trade-off. With the smaller sample, I'm less likely to catch those extreme values. But if I do catch an extreme value, it's going to pull that mean out a lot more. It's going to impact that a lot more than it would if I have like a larger sample. Okay. So the thing to be focusing on here is that it's going to jump around, right? But if I go through, Amanda, and I have sample sizes of 500, right? And I measure the mean height of sample size 500, how much are those going to bounce around? Not much. They're going to be all tight. They're going to be right up in here, right? Versus if I have a small sample, it's going to jump around more with that. Okay. And so again, if we think about our equation for our formula for our standard error, it's population standard deviation divided by the square root of my sample size. As that sample goes up, forces that standard error down. I'm going to think about it as having a more stable and consistent estimate, as opposed to a lower sample where things jump around more. Yeah.
But what's yeah is, I guess my question is, why for a larger sample would you not expect population?
Okay. So we're talking about different distributions. Okay. You're talking about a sample distribution.
Sample means, sorry, like why, like if the sample gets bigger, why would you expect more closely resemble the distribution of samples?
Okay. So you're saying, say that to me again, but tell me which distributions you're specifically talking about.
So for example, looking at the blue curve is a bigger sample. Why is it that the actual distribution closer?
Yeah. Okay. Yeah. So what is it in this distribution here? What are the units?
Okay, wait, I know where I made a mistake. I think I'm thinking about, I was thinking about population distribution. Yeah, no. Okay. Questions.
Okay. So what are the units in this population distribution?
Sample.
So This, so the population distribution.
Oh, it's a population distribution. It's
Individual distribution, right? So basically what we're doing is we have two distributions, but the units are different, right? Here, we just got individual people. Here, with all of these, our units are sample means, right? And so I wouldn't expect my distribution of sample means to look like my sampling or my population distribution, because I'm not measuring the same thing. I'm measuring mean of something versus single scores of something, right? And what we don't want, and so this is why we can use normal theory statistics to test things that aren't normally distributed, is because even if I've got something that has a wacky distribution, right? Like say reaction times or substance use or, you know, child aggression or something along those lines, right? If the sampling distribution mirrored the actual population distribution, that wouldn't give us anything because I'd still be working with a funky distribution, right? But because what we know is that the sampling distribution, if our methods are good, will equal sort of be normal. What we can then do is apply normal theory statistics to even things that aren't normally distributed, because even though, and this is like, oh, hey, this is the nice thing, or this is the normal curve here, and it kind of follows a nice thing, it doesn't have to. And that's why, if you go to this slide and hit that link up there, if you just really don't tell your family or friends, but so basically this is, again, me walking through and generating in front of you like randomly select or just randomly generated data, normal curve data, really skewed data in SPSF if you're interested in sort of how you can sort of coax that stuff out of there. So I'm just kind of walking through talking about this. What you see is what I do is go through and calculate, generate a population of scores and a big number of population of scores with certain sort of skew or sort of normal stuff, and then go through and tell SPSS to randomly estimate or randomly select with, no, I can't do it with replacement, even without replacement, just to randomly select a group of scores and then plot those means out. It's shocking how fast all this comes together and how the standard deviation, that sampling distribution very quickly starts to, yeah, it all sort of works out. I was shocked when I did it. I'm like, okay, I'll go through and do this and it'll probably be like, oh, well, in theory, this should work. It works in practice very quickly. So would encourage you all just to watch it. And I mean, seeing a demonstration of it with actual sort of data that's more than population size 4, it will help you start to solidify some of these concepts. Okay. Yeah, Elizabeth.
Kind of going on Sam's question with like the distribution. A sample mean, population, and sample are 3 different types of distribution.
Yep.
So, for my understanding, if we're looking at a population and sample distribution, is that us charting out the individual data point compared to the sample means is when it was to be replicate our samples, and we're plotting out the means of each of those.
Yep.
Samples. Is that the difference?
Yep. So we have here first distribution. We got the distribution population scores. Okay, and this is going to be sort of all scores in the population, right? It's going to have its own shape, mean, and metric of variability, right? And then I'm going to have a distribution of my sample scores. Okay, this is a subset of scores from the population. I pull that sample to represent the population, right? But it's going to have its own shape, mean, and variability. And then I'm going to have a distribution of sample means. This is a theoretical concept, right? This is the means of all possible samples of a specific size, also going to have its own shape, mean, and variability. Okay, so in actual fact, with the type of stuff we do, this is a hypothetical. That's a hypothetical. This is what we're left with, right? But when we go through and we take a look at what this actually looks like, so here, again, if we say IQ scores, population mean and standard deviation, right, of all scores. Nice, beautiful, normal curve. But then I go through and I get my sample of size 30. My mean's close, right? Teresa, what do I call the difference between my sample statistic and my actual population statistic? Sampling error, right? So I've got some sampling error. I'm not bad. Sampling error here, not bad. Actually pretty good for sample size 30. But is this a normal distribution? Not really. I mean, kind of ish. It's probably not terrible, but it's not nice and beautiful like this, right? but this is what I got. These are the scores that I was able to pull. But if I were to go through and pull all possible samples of size 30 with replacement from this population, what it would give me would be a distribution of sample means. That distribution of sample means now is back to this nice, beautiful bell-shaped curve with the expected value of the mean equal to my population mean, and the standard deviation of my distribution of sample means equal to the standard deviation of my population divided by the square root of my sample size, and that gives me my standard error here. And that standard error tells me of sample size 30, if I were to randomly sample individuals, measure IQ, I would expect on average scores to jump around by about just a little under 3 points, right? So from sample to sample to sample to sample, I would expect on average those to kind of bounce around about 3 points. Any randomly selected sample, I would expect to be about 3 points off. And if we go through and we take a look, we say, yeah, 102, actually doing here a little bit closer. But if I were to pull a different sample, it could be way off. It could be way out here, right? I don't know. It's not likely. All I have is just the one sample, but this is what I can go through and expect. Yeah, Katie.
I'm like understanding what you're saying, but I still feel like something is just not clicking for me. So I understand that these are like examples, but as soon as you hit like a sample size of 30 or more, will it like almost always be normally distributed, or?
It should. It should if I got random, if I have random selection and I'm measuring without error, and we'll get into this, there's a bunch of stuff that needs to happen that rarely does. But fortunately, a lot of our statistics tend to be kind of robust to things. And so we are able to overlook some of those warts so long as we recognize that they're there and recognize the potential impact of that. Okay. Okay. Let's do this. Let's go through, let's break. And when we come back, we'll roll back into some Z-score types of things, how we go through and use this to start inferring things about the likelihood of drawing a sample with given characteristics, assuming a known population. Okay, so let's come back 7:35, or excuse me, 3:35. I'm just shouting numbers on my watch. I said 12:98. Mics. Oh, whoops. Okay. Any last questions, I guess, for right now with our distribution stuff before we jump into using Z-scores for this? Yes.
I feel kind of silly asking something, but I'm going to do it anyways. So when I originally asked you back on the sampling distribution, well, the sample size and replication expected, and we said no, not really. But then for everything else, it is like the sampling size and replication expected. What was the difference in the very beginning when we said no, it happens naturally, compared to now saying that yes, those things do affect it?
Okay, so tell me again where we were asking about replications and things like that.
And I said, like on the scale on the left, or the graph on the left compared to the right, and then I said, is that because of sample size and replication? I said, no, that happens naturally.
Okay, the distribution, the distribution of sample means. So.
Oh. Sorry. Okay, so
Okay.
you saying that, can I tell you what my initial thought was?
Sure.
Is that with sample needs themselves, we already had to get, a calculator, a larger population size, and had to do replications in order to even get multiple sample needs. So now we already did the population size and replication. Now we're just taking what we have and applying it into the sample need distribution. So at this point, those two factors aren't going to change anything, but earlier on, the population and sample, those factors would have changed something.
Yes, yes. So here, if the question is does getting from here to here, do I have to do certain things with my sample size, population, things like that. No, like this is going to happen no matter what. Now the shape is nicer, and it gets nicer more quickly if certain things happen, right? As if the population from which I'm drawing samples is normal. Is that true here? No, this isn't a normal, but, or as my sample sizes start to increase. Now, here we've got a nice little constructive example where everything works out nicely. If I'm looking at, again, Elizabeth, what is your research area? What do you?
Geriatrics.
Geriatrics. I'm looking at cognitive impairment in older adults or something like that. It's probably something that's has a skew to it, right? If I am wanting to run some mean-based analyses, right, looking at medication on whether or not it improves cognitive ability, right? Cognitive ability in impaired individuals is not going to be normally distributed. And so what I'm going to need is I'm going to probably, if I want to have confidence in my test statistics, if I'm comparing my intervention and non-intervention sample, what I want to get is sample sizes that are sort of reasonably large so that I can start relying on the distribution of sample means across those things. Is if I don't, then my distribution of sample means probably isn't going to be normal for, like, say, sample size 10, and then I'm going to have weird stuff go on and it starts to erode my confidence in my test statistic. But it'll get there as I get larger and larger samples, right? And so when I was saying, yeah, it doesn't make, like, sort of this is going to happen regardless, it will, but under those two conditions where we're talking about approaching normality. The thing where it does make a difference in terms of what sample size I'm using here, we're kind of limited. Our samples can be either 2 or 3, because 1 is not a sample. 2 and 3 are the only two values less than 4. So for this constructive example, I don't have a lot of leeway on what I choose as my sample size. But as we start doing our sort of actual research, then we can start to choose, right? And sort of as that sample, as samples get bigger, what happens to the stability of my estimates? Increases, right? Or my standard error decreases, the extent to which I would expect my sample to be representative of the actual population mean, assuming some stuff is going on, gets closer, right? And so then that's what gives us additional power to tease out differences in our stuff. So when you're saying, does it make a difference? It kind of depends on what we're talking about. Like, will it hit this? Yeah, it will. As our sample sizes start to go up, what happens is it reduces that error. We get more precise estimates. You're going to hear me talk a lot about harping on precision and things along those lines. We get more precise estimates. And then if we're thinking about replication in terms of Matt runs a study and Basha runs a study, how close those two things are together. Those two things are more likely to be together, assuming they're using the same methods, pulling from the same population and things, if they've got bigger samples than if they've got smaller samples, right? Replication is what we're talking about here. We're talking about all possible replications or all possible samples of size. This is a different type of replication. It's kind of like a theoretical replication type of a thing here. So this is all possibles. That is those two. And so we've got a little bit of a difference there. Okay. All right. So sit on this. And if you have questions, and again, that some of the chapters and the readings and stuff like that are good to, it's kind of hard to pick some of this stuff up on the fly. But if you're going through sitting with it, and like if you're me trying to understand, like I've got sort of notepad, I'm like sort of drawing things out and sort of things along those lines. So, but come find me if you're still struggling, because this is, again, super, super important to kind of have a concept. Because if you don't have a good handle on this, everything else that we're talking about will seem a little bit fuzzy. Okay. All right. So let's get into sort of why we're doing this all in the first place. So primary function of our distribution of sample means is going to try and we're going to use these and use our statistical techniques to try and find a probability of selecting some random sample with certain characteristics based on some assumed model. And I asterisk the hell out of this because this, based on the assumed model, we need to start thinking carefully about what that assumed model is and kind of what's happening here, okay? So what we're doing was we're essentially asking, what's the probability of randomly selecting a sample with mean M, assuming a normal distribution of means, right? And so this is where we get away from population scores and into sample means, right? Because population distribution, right? I may not know, and I may not be know what exactly what the characteristics or the shape of that distribution is. But do I know the shape of the distribution of sample means? Yep, it's going to be normal. So now I've got a known distribution with known characteristics that I can start working with. Okay, and so what we can do at a most basic level is use start to calculate z-scores for sample means. Before we were using calculating z-scores for individual observations, what we're doing now is we're going to calculate z-scores for sample means. And what we can do is we can use the same methods we did before to start making a determination or making assumptions of how likely it would be to draw a sample of size n with characteristics mean, standard deviation x based on some assumed distribution of sample means. Okay, and our z-score here, identical to what it was before. Only thing we did is we swapped out instead of x minus the population mean, it's just the sample mean minus the population mean over, instead of our standard deviation, this is just our standard error. Okay. So we just went from scores to means. We just kind of shifted distributions over. Okay. And so what we can do now, before when we were saying, how likely is Teresa to pull someone with a score of X or higher on an IQ test, sort of given to the distribution, known distribution of scores? What we can do now is start extending that out to samples. So we could say SAT scores form a normal distribution, 500 to 100. What's the probability of selecting a random sample of 10 students with a mean SAT less than 440? Okay. We're not talking about individual scores, we're talking about samples, right? But we can use the same procedures, right? We could also identify the likelihood of selecting a random sample of 75 students with a mean SAT score of less than 440. If the population mean is 500 and this standard deviation is 100, which one of these scenarios is more likely based on what we've talked about up to this point? Am I more likely to find have a sample of 10 or a sample of 75 that has a mean SAT score that's less than 440? Josiah? 10. Yeah, why? Exactly.
The smaller number has the smaller number.
Okay. Standard. There you go. Okay. My smaller sample, I'm expecting that to jump around a whole lot. So to get 10 people with a mean value that's 0.6 of a standard deviation below the mean, I mean, maybe, right? Probably not super likely, but maybe, right? But what if I jump that up to 75? I'm going to go through randomly select 75 students who are consistently scoring 0.6 of a standard deviation below the mean. This is probably very unlikely, right? And so what we can do, instead of relying on individual values, what we're doing is we're starting to play around with samples. And if, let's say, this is maybe in this situation, and I know this is a terrible, like, sort of not a study that you would do, but let's say I'm interested in the impact of soccer or American football on cognitive ability and performance and things like that, right? And so my assumption is that getting your head and brain knocked around is sort of may have an impact on sort of your SAT scores, right? So if we're assuming that people who participate in soccer and or football have a distribution of SAT scores that's equal to the population, if I find a group of football players with scores that are consistently lower, that would be consistent with, like, that would be a very rare thing to happen, right? And so what I might start to conclude is that maybe this specific subpopulation I've drawn from has a different distribution, sort of mean values, than sort of the larger population of individuals, okay? And so we're going to start to use this to start making inferences about certain types of things, okay? Now, when we're seeing patterns in data, this is an incredibly important slide, okay? Always, 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 I don't know, I talk about this in my clinical supervision about having multiple hypotheses, right? Sort of, okay, I'm not trying to wed myself to any one specific interpretation. What are the possible interpretations of this? Anytime you see patterns of data, one could be patterns caused by a systematic factor that reflects some true effect, Okay, this is what we're always hoping for. This is why we're doing the research. This is what we're hoping for. It's really easy to get drawn into this, right? Like, oh, the group I expected to score higher is scoring higher, and so that's therefore evidence of my theory that something's going on, right? So we like that one. But it's possible the pattern is a result of chance fluctuations, okay? Not representative effect. It's just like on this sample that I happen to catch, this group happened to score higher than that group, but if I were to do it again, it would maybe be flip-flopped around, right? Last possibility is that we're getting some pattern that's the result of systematic bias, violations of underlying statistical models, and then that starts to be no good, right? We start to get sad. We get spooked by that. Why? Because we don't know what distributions we're working with. We're good and we're happy when we have known distributions that we're working with. If we start violating our assumptions of our underlying models, all that stuff that we talked about distribution of sample means and known characteristics and stuff, that goes out the window. That's why we're always wanting to be checking our assumptions and saying, okay, these data are the data that I could get. What are the potential flaws? What are the potential warts? Sort of where are the things going so I can provide accurate estimations of my stuff, okay? And so our null hypothesis testing, in theory, should help us start to give us procedures, start to tease apart statistical inferences. And what we're trying to do is use these methods to go and say, are the patterns that I'm seeing in these data, are they likely due to some systematic effect, or is this just a function of just random fluctuations in my data? Okay, am I seeing patterns when there are no patterns? There's a whole area, we talk about this in PSYC, right? Sort of our ability to see patterns where they're not patterns gets us into problems sometimes, not just in science, but in sort of general in life. There's a lot of conspiracy theory stuff, but we're trained visually to see patterns, right? Sometimes though, those patterns aren't there, and we need to be aware of that and try and have some methods that help us make important decisions, okay? But the important thing to remember here through all of this is we don't have a statistical test that tells us whether or not we have good methods. We got to sit back and think that I can't run a chi-square to see if Josiah did a good job with his thesis, right? Like I have to look at what he did, think about, is this plausible? Can we answer the question that he wants to answer? This is hard work and it requires thoughtfulness. There's no p-value for this. But if those methods aren't good, then we have a real hard time drawing anything, making any interpretations from the statistics. And so if we're going to use this, we can't divorce this from methods. We always have to be considering sort of what's going on. Is what people did reasonable with this? Okay. All right. Oh boy, that was just to spook you. To get you, keep you on your toes. You never know where that's going to come at you. All right. So if we're talking about hypothesis tests, okay, this is our procedure that we use to draw inferences about some unknown population value. Okay. So assume that so the most simple sort of scenario is what we'll start with. If we assume that some population has some mean or sort of some value, right? What we're wanting to do is look at the probability of drawing a sample from that population with a mean that's at or more extreme than the one we observed. Okay, so in this situation, let's say we're doing rat work, right? And I've got a population of rats, and these are sort of genetically sort of pure rats, so we know kind of exactly what the parameters of rat parameters are here, right? And so this population rat, say we know as a mean of 400 grams, okay? If I pull a population or a sample from this population of sort of known rat weights, my sample should be somewhere around 400 grams, right? But maybe what we do is we take this population and we apply some treatment. We do something to it. Now this is a population of treated rats, which is different than this population, right? Now, if we assume that this treatment had no impact, then the population weight of the treated rat should be equal to the sort of known rat, right? Nothing happened, right? But if I go through and I pull a sample of rats and I give them this treatment and then I weigh them, right? And I look to see how likely it is if this population, this new population of rats that I created, because I gave them a treatment, right? If my new rats have a weight of say 300 grams or 500 grams, how likely is it that I would get a sample size, a sample of size X or a sample of size N from a population with a known mean of 400? How likely would I randomly select someone with a population or a sample with weight 500 grams or 300 grams or what have you? Okay, and so this is what we're doing. We're if we go through and we determine that it's a very low probability, right? It would be uncommon to randomly draw a sample with these characteristics, assuming that this should be the parameters. Then we would generally conclude that this population has some different mean than what we would expect here, right? So if I go through and I find that my population of treated rats or my sample of treated rats has a mean value of 500, right? I would say, and let's say I've got a decent sample size, say sample size 50. I would say, boy, if this population of treated rats truly had samples, a mean weight of 400 grams, it would be very, very rare for me to grab a sample size 50 that had a mean weight of 500 grams. Okay. And so in that situation, what we would likely do is we would likely conclude that the new population of treated rats has some different value, mean value, than our original population. Okay. And Emily, if I pulled a sample and the sample weighed 500 grams, what's my best guess for the true population weight of those treated rats? 500, right? Because I'm assuming that my sample is a reasonable sample from this population. And so I would say in that situation, maybe that no, it appears that based on the data that I've collected, that this treated rats has a different weight of 500 grams, right? And so then maybe I would say, yeah, this treatment has some effect. But if I were to go through and find that my mean that I pull from my treated rats is somewhere in the vicinity of 400 grams, then I might make the opposite conclusion. I might say, well, I don't have enough evidence here to conclude that that this treatment has any impact on rat weight because my sample has something that's maybe not exact, but it's something close enough, right? That I would say, yeah, it might not be super common, but it wouldn't be unreasonable to extract a sample given these characteristics based on what I'm looking at here. Yeah.
The point of all this, like, just kind of like gather the outliers and normal distribution.
Yep, a lot of it, right? And this is where in applied research, you're always looking at your distributions. You're looking kind of what your scores are looking like. You're saying, hey, does this look reasonable given what I know about ADHD? And if I look at it, I'm like, nope, that doesn't seem right, right? Like, so everybody in my sample has a GPA of 1 or something like that. I'm like, well, I know ADHD impacts GPA, but probably not to that level. So now I'm going to start to be wondering what's gone on and things along those lines, right? So again, just the analyses, and this is, people get really worked up about what numbers that I get and what the values are. That's such a minuscule piece of the whole process, right? It's sort of something that happens kind of at the very end. The bulk of the work and all the good work happens on the front end, making sure that your methods are good, your data are clean, and things along these lines. Yeah. All right, so we got an example. Okay, so we researchers believe antioxidant supplements may reduce and possibly reverse age-related cognitive decline. So we got a new ginseng something or other that we were saying, hey, this is going to fix age-related decline. So we take a sample of 25 adults, age 65 or over, and we have them take these antioxidants for a period of 6 months. Okay, participants are given a neurological test to assess cognitive functioning. Scores for the test are known to be normal in the population with adults 65 or older, scoring a of 80, standard deviation of 20. Okay, so in this situation, we have a well-normed measure where we know what the population mean and standard deviation are for this specific group. Okay, before anybody asks, this is rarely the situation that we're dealing with in actual applied research, but this is where we're going to start and we'll build on that as we move forward. Okay, but in this case, so basically it's the same thing as like an IQ score or something like that, where we have a norm, mean, standard deviation, and we know that individuals 65 or older have a mean score of 50, standard deviation of 20. Previous psychometric research suggests a change or difference in scores exceeding 10 or more points is going to be practical, right? So if we get a difference of 10 points or more, that's something that we can kind of say, oh, hey, this actually has clinical or practical relevance to this situation. Okay. So if we're going to run our hypotheses test, first thing we need to do is we need to state our hypotheses. Okay. What we're doing here is we're predicting the characteristics of a sample to be collected, not one that I already have and I've already looked at, because that screws things up. Something that's sort of out there in the future that I have not yet collected. We're going to set a probability criterion for determining a reliable effect. We're going to collect our sample data, compute relevant statistics, and then we're going to draw conclusions about the behavior of population based on the data that we have. Okay. So, all right, step one, stating our hypotheses. This is a lot harder than you think it would be, because what I'm going to be asking you to do is demonstrate that you understand exactly what we're doing in this situation. Our statement of a hypothesis, and this is probably going back to undergraduate statistics, hopefully, statement of two related hypotheses. Our null hypothesis is almost always going to be involves some zero association between the IV and the DV in the larger population. Okay, the manipulation has no effect on the outcome. Okay, something along the lines, and what I'm going to ask you to do is tell me exactly what that null population is or that null hypothesis is by being explicit and telling well, what the relevant population, what the base population is, right? Because I can just say, oh, scores will be equal to 80. Scores of what? With whom, right? We never do this, but like I'm going to ask you to do it because it's going to force you to think carefully about who are we trying to draw inferences about, what's the population we're trying to generalize to, what are we measuring, and what does all this stuff mean? Okay, so this is our null hypothesis. The null hypothesis is always going to be nothing's going on. So the sample that we've drawn or the subpopulation we're interested in is the same as everybody else. Nothing to see here. Okay. Our alternative hypotheses, we can sort of generalize this to say some non-zero association exists between our independent variable and dependent variable within the larger population. Okay. Why do I keep talking about associations between the IV and DV in the larger population? Why?
Because we're using these.
Okay. Okay, right. So we're interested in, so we're talking about making inferences about a sampling distribution. Yeah, what else?
I don't know if this is right, but is it because when we're doing hypothesis testing, we're not trying to just look at that one sample?
Yeah, exactly. I don't care about the sample. I don't need statistics to tell me whether, if I say in this example, as I'm saying, my null hypothesis is that, and it would be incorrect to say my null hypothesis is the mean of the sample will be 80, right? Do I need statistics to tell me if the mean of the sample is equal to 80? No, I just look at it. If it is 80, then it's 80. If it's not, it's not. I don't have to do anything if all I was interested in the sample. But I'm not interested in the sample. I'm only interested in the sample so far as it's a representation of some population of interest, right? And so if that sample mean starts to deviate far enough away from my assumed population mean to make it seem like that would be a unlikely thing to happen if the true population mean were this, then I start to sort of make some different decisions as opposed as if it's close. We don't care about the sample. Sample is a means to an end. Never in your statement of a hypothesis should you ever say the word sample. No one cares about the sample. We're always talking about populations because that's who we're trying to make inferences about. Okay. So again, our null hypothesis, no difference, no effect, no association. Everything's the same. Alternative hypotheses means that there's some association, there is some difference. What I'm saying is not going to be equal to some reference value. Okay. Now, with our traditional null hypothesis testing, our null test is the only thing that we're interested in here. We kind of put in the alternative hypotheses just so that for completeness, but the only thing that we're testing here and the only thing that we can make statements about is our null hypothesis. Our null hypothesis is the only thing that we're drawing conclusions on. okay? This starts to get very tricky, and it sort of goes against what we would like to do, but these are the rules of the game, and we need to play by them and sort of keep them in mind. So a lot of the stuff that we're talking about is sort of talking about statistical models, okay? And we think about statistical models, a lot of times we think, oh, like an SEM or something along those lines. In a more general sense, our statistical model is just a set of assumptions outlining exactly how a sample of observations might have been generated, okay? So if I have sort of these data, sort of my statistical model, my working model involves all the assumptions about how these data came to be, what happened in terms of determining the shape distribution, things along these lines, okay? How we go through and think about and approach our null hypothesis testing almost always are restricted to some point estimate of the null, right? The mean, the population mean is equal to this, the population association is equal to 0, something along those lines. That null hypothesis almost always is going to be something is equal to 0 or something is equal to some specific value, okay? But in actual practice, if we're thinking about what's going on behind the scenes, even though I might say so that the mean difference between group A and group B is equal to 0, underlying that, what we don't think about a lot of times is a whole lot of other sort of things that are going on that are being assumed about how data from sample B and sample A and sample B were generated. And we can think about these as implicit assumptions, auxiliary hypotheses, auxiliary theories, things that are included here that we never think about, but always should be keeping in mind are things like we're assuming that data collected from sample A and sample B are representative of their respective populations, okay? We're assuming that our sample was randomly selected for each one of these. We're assuming that the distribution of sample means is normal if we're doing means-based testing. We're assuming that our model is correctly specified, that I actually am testing against a proper null as opposed to some other value. I'm assuming that my measures are valid, that the thing I use to measure the thing that I wanted to measure is a valid instrument. I'm assuming that my measurements were collected without error. Does that ever happen? Nope, right? I'm assuming that my hypotheses were generated prior to the evaluation of my data. We fudge on this sometimes. I'd be like, oh, after I go through and I got the data and I looked and say, oh, this sample is much different than that sample. That makes, yeah, no, those are the samples that I was really interested in the whole time. It's like sort of this group and that group. Yeah, I like that. Here's my a priori hypothesis that these two samples. Well, you've screwed it all up. Right now, all of our methods tank because what you've done is you've inserted prior knowledge before you decided to make your prediction, and that sort of ruins the whole statistical model. If we look at this stuff, we almost always violate a lot of these underlying assumptions, right? Our statistical tests work perfectly if these things are there. These things are never always there. And so we have a flawed system that we need to be very careful with in terms of making inferences. Our samples are almost never representative, right? Sometimes, but often not, depending on who our population is, right? And so this is where, Sam, if we're talking about like sort of saying, I don't know why I pointed you out, like not that you sort of were trying to argue with me, but let's say when we're talking about we're making statement on hypotheses, right? This is why I like you said, telling me what who do you think this should be generalizing? Who are we trying to capture, right? Because if I'm interested, Josiah, what's your motivations, stuff like that with Sean, or not?
I'm
With Ben.
But yeah, like goals and then like social identity stuff.
Okay. So goals, social identity, and things along those lines, right? Probably in theory, what we're thinking about is like how do humans develop goals and identity and things like that. Who's almost always going to be your who are you almost always going to sample for this type of research?
Well, a lot of it samples like undergraduate.
Yeah. Okay. So let's say is it possible that undergraduate goals, how they go through and develop things and sort of their sense of self is different in certain types of ways than, yeah, right. And so, but rarely do you say, oh, what I'm interested in is how sort of undergraduates, specifically freshmen, identify themselves. Like, no, we sort of present this as a universal thing when in fact our data only speak to sort of probably, well, depending on how generalizable this is, data drawn from a very specific subset of a specific subset of a specific subset of the human species, right? And so it's really easy to forget all that stuff, but it speaks directly to the representativeness of my sample, right? And we go on with all sorts of different examples like this along these, and starts to become very important as we're making interpretations. Random selection, that never happens. Distribution of sample means is normal, that we can get that to happen. Model is correctly specified, sort of depends. Measures are valid, hopefully that we can go through and choose instruments that have known psychometric properties. Measurements are collected without error, that never happens, right? I mean, this screws things up, but all things being equal, hopefully it's random and it just attenuates our effect size and it just hopefully just adds static to the model as opposed to pushing things one way or the other. Hypotheses were generated before evaluation, but this is something we can do, often don't, but need to be mindful of this stuff, right? So this is all the stuff that's being assumed that we're doing in the background that we're almost always never doing. And as soon as that starts to happen, to the extent that we start to deviate from these assumptions of our underlying statistical model, we start to be more cautious about making strong inferences about our data. Okay, so again, our estimates predicated on the underlying assumptions, both are explicit and explicit assumptions. And so this is why when we're going through and evaluating research and doing our own, need to be thinking about this and the potential impact that it can have. Okay. So for our supplement example, we're going to say for our null hypothesis, we'll say so the couple different ways we can state this. We can use statistical notation as kind of quick, short form, easy way, and then we can say it out in words. I'm going to have you do both. Short form statistical notation, the mean of the supplement group is going to be equal to 80, because that's what our population mean is, sort of known population. We're just saying nothing's going on. Supplement use doesn't do anything. This new population of supplement users have the same cognitive score as sort of everybody else, right? And so we say maybe the average cognitive functioning score in the population of older individuals using herbal supplements is equal to 80. Okay, so notice that I'm sort of not talking about the sample. I'm representing, saying my sample is representative of a larger population. This population that I'm pulling has a score equal to 80. Yeah. Nope, still thing, because again, we're talking about comparatively change over time within the population. Still don't care about my sample. Sample's just a means to an end. We're sort of cold, callous in terms of our participants, right? We're just using them to try and infer something about a larger population. My alternative hypotheses, pretty easy, non-directional hypotheses, which we generally use. Supplement, meaning the supplement population is not equal to 80. Average cognitive function in the population of older individuals taking herbal supplements is not equal to 80. Okay, pretty straightforward. But again, seeing what we're doing is putting the focus on populations, and I'm saying who I'm talking about and who I think my data represent, as opposed to just some short form equals 80, not equals 80, so on and so forth. Yeah. I will tell you, people will lose more points in this class for not getting this right than is reasonable. Okay. And it kills me because I sort of will flag it again. CJ, how often do we ding people for not being clear in their hypotheses? Oh, a lot, right? It's sort of the same thing over and over again. Anytime we're seeing statement of population, wanting to see it's a statement of hypotheses, I want you to tell me who are we talking about? Who are we trying to generalize to? Who are we trying to infer things about? Okay. We don't ever do this in actual research or studies. And if you did this in a paper, like someone would look at you like you're a weirdo, probably, but I don't care. I want you to know that you understand who we're talking about with these methods. All right. Then what we need to do, we need to set a decision criteria. Okay. This is going to be the probability of obtaining sample data, assuming that our null hypothesis is true, that would allow us to say, oh, this is likely or unlikely. Okay, this is kind of our decision point here. If we find our sample mean to be much different from our proposed population mean under the null, what we were likely to do is we're going to interpret our that our data that we've collected is incompatible with one of two things, either the null hypotheses, right? The data that we've collected is not compatible with the hypotheses that the population or the mean cognitive score in older adults taking supplements is equal to 80, right? So our data are inconsistent with the null or the assumptions of our underlying statistical model, which is that whole list of other things that we've gone through. I can find data that are inconsistent with my proposed population mean because of actual effects in the universe, or because I've just done a really kind of terrible job of collecting data. My statistical test doesn't tell me which one of those things is going on, right? And so again, this is why it's always important to go through, look at both in our own data, other data that we might be using, whether or not should these underlying assumptions are problematic. Okay. For example, what's your area? What's that? Jury decision making. All right. So let's say that you go through and you run a bunch of jury studies, and you sort of make the conclusion that introduction of some type of evidence has no impact on decision making. But come to find out, and so you're saying that, hey, legal system, we no longer have to worry about this thing because this makes no impact on juries. The decision is all the same. So no need legal teams to worry about this thing, right? But if I go through and take a look at your study, it's all done with predominantly white women age 18 to 21 at the University of Wyoming. What's wrong with sort of where you've taken your interpretation given your methods? Yeah, it's not the sample that you pulled is not representative of who you're trying to speak to, right? And so what we've done is we've violated an underlying assumption of your model. Now, if you say, hey, if you happen to be presenting to juries of white women, predominantly white women from the University of Wyoming, who were University of Wyoming students age 18 to 21, then maybe that's a sound interpretation, right? But it's probably not, because that's not what real juries are made of, right? And so you need to start to be thinking about, so what we've done is I might find something that's very discrepant than sort of my null value, but it's maybe not because out there in the universe of juries that's a thing. It's because I've violated a bunch of my underlying assumptions, right? And so that's why I'm seeing the difference or non-difference as opposed to an actual effect, right? So always remembering that just because I find an effect doesn't mean there is one. There could be a couple of different things going on. That's why I have to go through and think carefully about what I've done. Okay. Sample mean similar to the hypothesized population mean. We're going to interpret this as generally compatible with the null. Okay. Our null testing tells us whether or not our data are unusual under the null hypotheses, but it doesn't imply that any the null model or any aspect of that null model is correct. So again, we find all the time with stuff is that people will say, oh, I didn't find an effect, therefore nothing to see here, right? Doesn't say that. Doesn't say that the null model is correct. It's just saying that we don't have evidence for the correct, for the null. We can say, yeah, these data are unusual given the null hypotheses, but the absence of an effect doesn't say that there isn't one, right? And it doesn't tell us that our null model is true. Nothing about this tells us whether or not our underlying theoretical model is true. It's just telling us we have evidence for or against, or something that looks consistent with the underlying assumptions. Okay. So our threshold for statistical significance is determined by us, kind of, not really. Technically it is, informally it's not. This is just our alpha level. So this is our probability threshold used to define our critical regions, where we're going to say, if we get beyond this point, we're going to say that the data that we observed is unusual or unlikely to have occurred if sort of the null hypothesis were to be true. Okay. Say that we sometimes get to choose that we convention sets. What is our alpha generally set to? 0.05, right? What if I went through and I tried to publish back, CJ's CJ's dissertation, he's like, hey, I'm going to go through and sort of my alpha levels 0.15. Committee going to say, nice try, unless you got a good reason for it. And there are sort of reasons for maybe extending that out, right? But probably not. We're not going to get away from it. We can go sort of more conservative, although there are problems with that. But technically, we get to choose to say, okay, this is where I'm going to determine that these data are unusual or unlikely. Okay. So going back to our supplement example, this, let's say, is our distribution of sample means, assuming the null is true. So assuming that the null hypothesis is true, that the population of older individuals who would be taking supplements has a mean cognitive score equal to 80 for whatever sample size we have. This is my distribution of sample means, right? What I would then do is say in this distribution of sample means, sort of what points cut off the upper tail and the lower tail of that distribution, where things would be very, very strange if they were to fall, not very, very strange, or at least unlikely to some extent if they were to fall in these ends of the distribution. And here we've got, we'll call it alpha equals 0.05. All right, then we'll go through and calculate our statistics, okay? In our most basic fundamental scenarios that almost never occur in out there in the wild, we're comparing data collected from our sample with some known population parameters. Okay, how often do we know population parameters? Almost never, right? But so in terms of understanding kind of what things are going on, we'll start assuming that we know population parameters, things like the mean in older adults age 65 or older in the larger population is 80 with a standard deviation of 20 or something like that, right? Just for illustration purposes. Our confidence interval, this is just going to be our sample mean, plus or minus our Z critical value times our standard error. Our test statistic here is just going to be calculated to find where our sample mean is going to fall relative to known population means relative to the known population mean based on our assumed null hypotheses. So my test statistic here is just going to be the mean minus my population mean over my standard error. Standard error, again, is just my population standard deviation divided by the square root of my sample size. How are we feeling about this? Kind of following along, seeing what we got going on here? Okay, cool. So, and again, with these things, always sort of look at these equations, right? I think sometimes people just kind of zone out and be like, oh, these are the things that I put in to get an output. But if we took a look at this equation conceptually and say, here in the numerator, we've just got the difference between the sample data and our assumed value of the null, right? This is just giving you the distance. I mean, this is a raw metric of effect size. How far, how discrepant are my sample data from what I assume is the population value? Right? It's just a measure of distance divided by my standard error here. This is just the expected difference between a randomly selected sample mean and the population mean under the null. Okay. Again, my sample mean, or excuse me, my standard error is just the standard deviation of my sampling distribution. It's telling me for a sample of this size, if the null populate, for a sample of this size, how far would I expect some randomly selected mean to fall from the actual population mean? Okay. So Teresa, if I see that I have a sample mean that falls quite a long ways away from what I would expect under the null, and my standard error tells me that I should see not a whole lot of jumping around in terms of estimates of the population mean, what's my Z score likely to, is it going to be bigger or smaller? Be bigger, right? But if I was my numerator, so my observations not the same, but around to what I would expect. And we got a situation where my standard error says, oh yeah, so across samples, the standard deviation of my distribution of sample mean says that with a sample of this size and an assumed population variance of this, I would expect big jumps. What's the my Z test going to be? Maybe smaller, right? And we'll probably be less likely to find or conclude evidence for sort of the difference that I'm probably interested in, right? So again, thinking about these statistics, what's actually going into them, right? If I want to sort of increase my likelihood of confinement effect, I can do things to try and increase the likelihood of that deviation, right? And then I can go through probably the biggest thing is driving down that standard error. How do we drive down standard error?
Increase sample size.
Increase my sample size. My sample size goes up, standard error goes down. That's going to increase the power of my test. All right, so for our supplement example, let's say we want to calculate a Z statistic if I have people taking antioxidant supplements. I got a sample of 25, score an average of 92 points on my neurological assessment. So, and assuming again, that I have a population of 80 and standard deviation of 20 in adults 65 years of age or older. Okay. What I do is I got my mean, my sample mean is 92. I'm going to first calculate my standard error. Right? Standard error is just my population standard deviation divided by my sample square root of my sample size. Give me a standard error of 4. I only conduct research where things turn out to even round numbers. If they don't, I just throw the study away. Don't mess with it. If I can't do it in my head, I don't want to do it. All right, so we do that, and then we go through and we'll make calculators and statistic. Right, we take my observed mean from my supplement users, subtract it from my assumed mean under the null is 80, and then divide that by my standard error. Okay. And I get a value of 3. So again, going back to my equation here, I'm saying I've found a discrepancy of 12 points. My observed sample relative to what my assumed mean should be under the null. My standard error says that with a sample of 25 and a population standard deviation of 20, I should expect any randomly selected sample to fall about 3 units away from the mean. I've observed a value of 10, 12, right? You can start to see how that ratio plays out. I get a z-score of 30. And if I were to go through and plug this information into my confidence bound, I've got 92, which is my mean, plus or minus 1.96. This is my z-score that corresponds to my alpha equal 0.05. We'll get into that in a moment. We haven't quite got there yet. But this is just telling me, so if I'm calculating a confidence interval for using z values, alpha equals 0.05, always corresponds to 1.96. Okay. And then multiply that by my standard error is 4, and I get a confidence bound of 0.84 or 84.2 to 99.8. Someone want to be real brave and give me an interpretation of that confidence bound. Go for it, Emily.
Plausible that data applies.
Okay, getting there. Good. You got a lot of good components. Anybody kind of build on, sort of kind of fleshing that interpretation out?
Wouldn't that be if the null hypothesis is true?
Never say that. Yeah.
Or if it has no hypothesis, has no.
Okay. So hold off on that for right now, because yes, we can infer something about the null hypothesis. Basically, our confidence bounds give us all the stuff that we need to know about sort of what we would do farther on in the test. And like, but hold off on that. I don't want to get to there quite yet. Just the confidence bound, just sort of interpretive. So what can we say about this confidence bound? Or what we're measuring? Okay, beautiful. Love that. Only thing I would add to that would just be telling us what we're measuring here. So we're all very good, right? So we could say that so based on the data we've collected, plausible values or sort of reasonable values for the average score on this cognitive test for older adults taking supplements fall somewhere between 84.2 and 9.8. So Emily, you were on track, sort of both of you just wanted to sort of tell us exactly what's going on. So what are we looking at? Because then all of a sudden, if I start putting those words in, something magical happens. I have to start thinking about what that means. We can start to recognize kind of stuff going on. And so we're saying that, yes, based on the data that we've collected, any estimate, based on the data that I've collected, estimates for the average cognitive score in older adults taking supplements should range anywhere, could range anywhere from the lower bound of 84.2 to 99.8. Okay. What's our best guess, Teresa?
Our best guess is going to be the
Yeah, this is moving it.
92. 92 is our best guess. And if you put a gun in my head, I would say 92, right? But I would say anything from 84.2 to 99.8 would be reasonable. Okay. Now, Josiah, to get back to what you were picking up on.
I think I confused the two. I thought that was like the general population.
Oh, okay. Nope. Yeah. So 92 is what we got out of our adults with supplements. Population equals 8. Okay. So
We don't really need a confidence interval.
yeah, don't need. I mean, we don't, because it is this number, right? But thinking about what so the population of older adults has a mean value of 80, and this is my interval estimate for older adults taking supplements. What can I reasonably infer just based on that? Yeah, yeah. The supplement has an impact on intellectual assessment. Why? Why can I infer that from just that interval? Their population. Yeah. 80, right? And so if I say, Josiah, you tell me that based on the data you collected, means cognitive function for the population of older adults taking supplements fall somewhere between 84.2 and 99.8. And I say, okay, well, what about, could it be 80? What would you tell me?
And I did think that was a 3 too, right? The 3 tells us.
Okay, ignore the 3. Ignore the 3. Yeah, so you say this is my confidence bound for older adults, population of older adults taking supplements. I'm like, well, could it be 80? What do you tell me? Yeah, it's possible, but not like maybe. But the data that I've collected say that's not a reasonable guess, right? Best guess is 92, but anything to the lower bound, 84.2 is kind of negative. So already, just right here, do we need to go through sort of z-tests and p-values and all that type of stuff? Nope. It kind of spoils the end of it. We already know just looking at that, sort of whether or not we're going to claim evidence for an effect or not based on our alpha level, right? And this interval gives us actually much more information because it's just not like, yeah, it's bigger or smaller. This tells us exactly how much bigger and within what range. Gives us a sense of precision. Anything interesting that we could communicate that would have any practical meaning to people is all contained right within there, right? Now we're going to go through and do the hypothesis testing because those are the rules and things along those lines, but we don't need to because it's all right there. And more information and more useful information than just making yes, no decisions. All right, so, but let's change this up. So we're sort of feeling pretty good about scenario 1. Scenario 2, what's the statistic of individuals taking antioxidant supplements? Again, sample 25, scored an average of 84 points on the neurological assessment. Okay. So again, they're still scoring more, but not quite as much, right? Here, same thing, we've got our mean, calculate our standard error, that's the same, right? So our standard error doesn't change, it's still the same sample, still the same population, that's not going to change around at all. But what we have in our Z statistic is we've got a smaller discrepancy, right? Our data that we've observed is closer to the assumed population we wanted to know. Divide this by our standard error, and we get a Z value of 1. Okay. We go through and we calculate our confidence bound. Again, we've got our mean here, plus or minus. When I say do a lot of trouble, if you sort of write this down and circle it and sort of brand it into your brain, the Z-score that goes into your population or your confidence interval corresponds to whatever level of confidence, not this. This is your test score. This is your test score. Not this is the. You're gonna have two Z values. With all this, you're gonna have two. You're gonna have a test statistic and you're gonna have a critical value. This is your critical value, not your test. Someone will go through and plug a test statistic into the confidence interval that's going to throw you way off base. When we're working with our Z scores, this value is always going to be for alpha equal 0.05. It's always going to be 196. Get into sort of 0.0199% confidence interval, it's going to be 2 point. Yeah. So avoid sort of mistakes, sort of know that this is always going to be the same. Okay. But so now we go through and we calculate our confidence interval here. Amanda, what can you give an interpretation of this confidence bound right here?
So based on the data collected, plausible scores for older adults taking supplements.
76.2 and 98.1.
Yes.
Yeah, perfect. And again, this will sometimes end up feeling a little bit like sort of verbal gymnastics. So we want to say scores for what, scores on sort of this cognitive test, sort of kind of go, but play around with it. Because what we'll end up having is you get bored of doing this. It'll feel like I'm having you write your name on the chalkboard over and over again. That's not my intent. My intent is that to kind of play around with sort of using different words and sort of using different models to really solidify this. Amanda, you're right on base. And so we're saying with in the second scenario, exactly the same number of people, right? But what we're finding is that my confidence bound is running from a lower bound of 76.2 to the upper bound of 91.8. Okay. So, Asha, what can we conclude already just based on that interval estimate we've created?
Supplements don't do that.
That makes sense that you would say that, right? And we're going to get into this. And why would you say that the supplements don't make any difference? Okay, so basically, my assumed population mean under the null falls within there. 80 falls within my confidence bound, right? So when I asked Josiah, I was like, "Hey, what about 80? 80 is what could it be 80?" He's like, "Get out of here!" Like, no, I just told you these are values. In your situation, if I said, "What about 80?" What would you say? Yeah, possible, sure, right? Only thing we want to say when we get into this, we never want to say that this isn't the thing, right? That this that it proves the null, or that the null is correct, or that supplements don't have an impact. Because 80 is a reasonable guess. So is 91.8, and that's it, close to 12 points above our mean, right? And if our cutoff is 10, I don't know, right? Supplements might not have an impact, right? But they might. I don't know. So there's just a level of imprecision in this estimate that makes it all kind of ambiguous, right? So our knee-jerk reaction is to say, well, 80 falls in there, so supplements don't have an impact. But you've got an upper bound in this confidence bound that definitely would suggest an impact. So we're kind of left in this, I don't know, right? And it's okay to be in this. We don't always have to have a decision. We don't have to have an inclusive. And most of our stuff, anytime we get a null effect, it's always inclusive. Or we never prove the null. Use some stuff that kind of gets along there. But the best we can say is these data are inclusive. Maybe there is, maybe there isn't, but it's hard to tell based on the data.
You would always say it's inclusive, that you're just not.
Yeah. And that's the thing. Like we want to say, and this is we're all guilty of it, right? If we go through and we find a sort of we run a test and then we say there's has a large p-value, we say there's no effect. Technically, that's not right. We just say we don't know. We don't have evidence for an effect. You know, we can't claim evidence for this, but we're not saying that it's not there. Now, sometimes we can get very, very large samples, very, very precise estimates, and we can say it's probably 0, right? But this is not that case, and we're rarely working with the size of samples where we can do that. There's a whole area of sort of null testing or equivalence testing and things like that that's kind of interesting. but in general involves large samples and sort of precision estimates where we start to make some, get closer to getting to some of those conclusions.
For scenario two, you're saying because.
Well, there are equal amounts of precision in both areas. We just have sort of like not great precision. That's all might not precision in the first scenario is all above that assumed value rate, right? Here, my imprecision captures that null value. So we're saying, if I say, could the population of older adults have a mean cognitive score that's equal to just general older adults in the population? Yeah, I mean, my best guess is they're about 4 points higher, but students are random static. 80 is perfectly 80 would be a perfectly acceptable estimate. That's another question. Cool. So, scenario one, if we're doing like our classic undergrad hypothesis testing, what we do is we go through and calculate our curve. See, my alpha level is 0.05, my critical value is 1.96. Where did we get those? For the level for our confidence interval, yep. Actually, so this is just our Z table. If we go through and if we have our error level is 0.05, we've got 0.2025 in this end, 0.025 in this end, right? So we kind of split this. And if we go look on our Z table and find what Z value corresponds to 2.5% of top tail, 2.5% bottom, or 2.5% bottom tail, we're going to get this value of 1.96. Okay, so those are just going to be our standard estimates for Z tests. My mean is 92. Here's my confidence bound, and my p-value is 0.003. Okay. What we would do is if I go to, okay, there we go. So this p-value, I just got, so this down here is a nice little calculator that I like to use. You just plug in like all sorts of different values and it just pops out your p-value. This is a good thing to use this. Otherwise, in tables, you get sort of different value depending on which one you choose. Here, if we were to put a Z statistic of 3 into our calculator, online calculator, here we get a p-value for a two-tailed test of 0.003. Okay. If I map out where 3 falls in this distribution, it's way out here. Here's my cut point. And so we're saying this is falling within our critical region. And so we would make it a corresponding decision. Our other scenario, same situation, except for we've got a mean of 84. Alpha level is the same, critical value is the same. Got my mean, my confidence bound, but now I've got a p-value of 0.317. Okay. If I were to map out where my z-score falls here, it's falling within the body of the distribution, right? It doesn't hit those critical values, and so that's going to impact the decision that I make here. Ignore this. One-tailed test, two-tailed test. In short, one-tailed test, two-tailed test is almost always what you're going to get held to, right? You're saying if I find things that are way too far above or way too far below, I'm going to claim evidence for an effect. A one-tailed test, you're putting all your eggs in one basket. You're putting all your critical value on one side. There are situations in which this can be useful, but it's just not. I don't know. In anybody's content area, do they see a lot of one-tailed tests? It's something you don't see a whole lot. Basically, what you're doing is it sort of reduces the threshold. If you're calling your shot, if you're calling direction, it reduces the test statistic that you need in order to claim evidence for your effect. Problem is that you'll probably get accused of making that directional test after you already looked at it and what was going on, which is not an unreasonable concern. And so in some areas, people will do this, but it's not, I don't know, it's not worth the 15 minutes of taking to go through and sort of talk about all the nuances and things like that. So go through, take a look at those, but I'm not going to hold you to one-tailed test. We won't worry about this for right now. Okay, everybody okay with that? I wanted to make sure I wasn't ruining anybody's night. God damn it, I was He skipped over my, it was the only, they just showed up for the ones that tests. All right. So last step, we're gonna go through and we're gonna draw a conclusion about the range of possible values of our population estimate, precision, effect size, based on confidence intervals. Later on, we're gonna get into actual effect sizes. And traditionally, we got two decisions. One, we've got to reject the null decision. This is what we do when our test statistic falls within our critical region that we've identified. And what this is saying is it says that our sample data are unlikely, assuming the null hypotheses and all corresponding assumptions of our statistical model. We've done everything correctly, and we fall, get an extreme score that falls within those critical bounds. We're going to assume that these data that we've seen are unlikely, would be unlikely, assuming that older, the average cognitive score of older adults taking supplements was in fact 80. This would be very unlikely data to identify or to find in a sample of 25. And what we do then is conclude that our sample was likely drawn from a population with a different mean than that specified under the null. Okay, and we take this as incorrect support for our alternative hypothesis. Problematic, but that's generally what we do. Okay, so if I go through, I have a large test statistic that falls within my critical bounds. I will reject the null and say these data, assuming the null is true, it would be very unlikely to find this data. And so what I'm thinking then instead is that the population that I'm actually sampling has some value different than what we specified under the null.
So p-value less than 0.05 may be outside.
Yep. Yep.
Okay.
All right. Other decision we can make is fail to reject. Okay. Traditionally make this decision when our test statistic falls within the body. And basically what this is saying is that our sample data are plausible given the null hypothesis. Right? They said it's not exactly, but I mean, could be like super reasonable, right? In our second scenario, we're saying that based on our size of our sample and sort of parameters of the expected population, finding a score of 84, the sample size of 25, not that surprising. Basically, we're saying that we're concluding that the data we've collected are consistent with what we would expect of a sample of 25 come from a population having a true mean value of 80. And so what we do here is we say sample data are plausible assuming null hypotheses, and we conclude here specifically that there's insufficient evidence to claim an effect. Okay, and when we hear, it's very important we recognize this is a agnostic versus atheist thing. We're not saying it's not there. Okay, we're just saying that we don't have evidence for it. Okay? And failure to reject the null hypothesis doesn't prove that there's no effect. Okay, we never say, oh, particularly the types of samples that we typically run with, we would never say, oh, this thing doesn't exist. So this thing, this population effect is equal to 0. There's nothing going on. We would say, hey, we just don't know one way or the other. We don't have enough data. We don't have sufficient evidence in this study to say whether there is an effect or there isn't. We're just saying that we don't know. Kind of this thing, right? Which is unsatisfying if we spend sort of 2 years of our lives collecting data on something, and at the end of the day, like, I don't know, it's kind of a big unfulfilling shrug, right? But it's a more responsible conclusion than saying, oh, there is no effect here. And again, here from the Wilkinson paper, never use the unfortunate phrase accept the null hypothesis, right? If we've accepted the null, we never accept the null. We just fail to reject the null. We just say, I don't know, maybe the null, maybe a lot of other things too. I don't know, maybe all the things that are within the bounds of my interval estimate I collected, but I can't really say much beyond that. Yeah.
During the trade, you were saying you want to write papers not saying the word significant.
Uh-huh.
So is this the language you would be using?
Yeah, I'm going to challenge you all to go through and spend 2 semesters not using the word significant. And we'll talk about sort of the language we go through this now. I'm not saying, so this is an academic exercise here to try and help you understand how to talk and think about effects without defaulting in the yes no decision based on p-values. Now, what you do in your labs and in your areas and things like that is a completely different thing. I'm not gonna find you like publicly yell at you because I saw at one point you found statistical effects. But what I am saying is there are ways to talk about research that doesn't require that. And some of this thing that they assume, and we'll get into that sort of next week in my favorite part of one of my favorite lectures here. Okay. So that's Eric came up with that. That's all right. So Amanda, to your point, here is how I would go through and sort of a sample write-up for the data that we've collected here in these examples, without sort of falling back on statistical significance or some of these things. So you can all read it's there, but saying, just want to walk through this, saying point estimate of mean cognitive functioning population of older adults taking antioxidant supplements. So here what is I've said I've collected a point estimate of mean cognitive function in a population. I'm saying what I've done is sort of recognizing what I've done. I've calculated an estimate for this population. Was 92. And the study suggested scores ranging from 84.2 to 99.8, reasonably lower and upper bound estimates of functioning in the larger population. Okay, what did I do there? I gave you an interval estimate based on the data that I've got, so from my confidence bound, I'm saying, hey, this is what we can expect. This is my point estimate, but for these, based on the data I've collected, these are reasonable values. The probability of randomly selecting a sample 25 with an average functioning 92 or greater, assuming true population value of 80 is 0.001. Okay, that sentence, that's me showing off on that I can sort of interpret those p-values correctly. Don't focus on that like this. We'll talk about how I got there, but you don't need to worry about that. Test value falls within the critical region set by alpha 0.05, assuming no meaningful violations of assumptions we have on a statistical model. Conventional decision rules recommend rejection of the null hypothesis. But then this red part, this is fine. This is sort of the important stuff, right? We're saying important to note, however, that estimates supported by these data are compatible with meaningful elevations in functioning relative to general population of older adults, as well as lower bound estimates falling below the threshold of practical effects. Remember when we introduced this, we said 10. 10 was our mark. If you get something 10 or above, then that suggests a meaningful effect. Less than 10, who cares, right? So where does this data support offer support for higher assessment scores in older adults reporting regular animosity? Our data do say that, yeah, it looks like there is an increase. Additionally, determine the extent which elevations are consistent with my point estimate. My best guess is 12 points above, and so I like that, and that's my best guess. And so I would be okay saying that, yeah, we have some evidence for a clinically relevant increase in functioning here, right? But I also probably would say that my lower bound estimate, anything 84.2, that's still at least a plausible estimate of the population functioning, and that actually falls below that threshold, right? And so saying, yeah, I found something here, and it looks promising. What I need is I need more data to sort of be more certain on whether or not sort of this antioxidant or supplement use is going to have a meaningful impact on functioning scores. Okay. I'm not asking you to shit on your data all the time, right? But what you probably should do is know exactly what you can say based on your data and what you can't. And hopefully anybody reviewing or looking at your data will appreciate the fact that you're building in some of that uncertainty in terms of sort of what you're doing. I think we feel like pressure all the time to say, this is the effect and so this is what it is, and start making a lot of grandiose interpretations of what's going on. It's rarely going to be the case where we can go through and do that, right? And so this is kind of where we're kind of doing some of that stuff. And so did you people see kind of where we're taking that interval estimate, sort of making a meaningful interpretation of that beyond just saying like, oh, the interval doesn't contain a null value, and so that means we have a significant effect, right? Which is how people tend to use interval estimates, which is an underutilization. Comfortable with this? Okay, scenario 2, okay. Here, a little different thing. You say supplement use in older adults was used, was associated with an incremental increase in cognitive function, which is bigger than 80, right? Relative to scores from the general population. However, plausible estimates of functioning in the target population based on these data range from 76.2 to 91.8. Probability randomly selecting. We say this score falls outside the critical region set by Alpha 105. Assuming no gross violations of assumptions in the unbox, this is the model. Conventional decision will create a failure or objective. Okay, so that's just like yes, no decision making, but that sucks, and so it doesn't tell us a whole lot about much. We say here that although data are compatible with estimates suggesting meaningful elevations of function, my upper says 91.8. That's some ideas are suggest that that could be a possibility relative to the general population. Study is at best inconclusive with respect to statistical practical benefits of supplement use. A lot less than we know here, right? We're just saying that based on the data that I've collected, individuals, older individuals who are using these supplements could have scores anywhere from about 76 to about 92. And so maybe it could, it's not saying it doesn't, it might have an actual, not just above 80, but actually could have some meaningful effect. But based on the information that I've collected, I mean, it's not no, but so what I would do is it looks like at least my estimates are saying maybe some incremental gain, but it's hard to sort of make them sort of claim that so this is knowing so much of anything. And it could even be associated with incremental decreases in cognitive functioning. That's equally plausible as 96, there's 76 is equally as plausible as 92. So we got to take the good and the bad and sort of think about sort of where we're at with our interpretations. You will see how, and this is an example, you notice across these two examples, I'm kind of changing up how I'm, so it's not just a cut and paste sort of robot sort of incantation on sort of how to interpret things. Just trying to change it up so that we can then be sort of focus, changing the emphasis on how we're presenting stuff. So type 1 error, we'll finish this up and then we'll be done. Will be exactly where I want to be. Type 1 error is what happens if we reject the null hypothesis when the null hypothesis is true. This is essentially us claiming an effect when there isn't one, right? Historically, it has been associated with the selection of an extreme sample. Okay, this is the one in science we're all worried about, right? Kind of jerks in science. We don't want anybody to get credit for anything that they don't deserve, right? So you can't. I don't want you claiming an effect for something if you really didn't find an effect, right? But if I do this, this is my type 1 error, right? I think again, the classic example would be again all those, and it's not that experimental folks are doing anything different than clinical folks. They're just taking it more seriously than we have, right? I run and publish a study that finds some effect. It turns out that my effect is way out here on the tail, when this is where the actual effect is. But if I'm around this area, I don't get to publish anything. But if I get this weird sample out here, I do. And now everybody just assumes that this is the case, even though people have been trying for decades to replicate that. No one's been able to, but we don't know that because no one's been able to publish it, right? This would be our classic type 1 error. Right? Katie didn't do anything wrong. She did everything right. She just randomly managed to collect a sample that's out here. This is where we would find our traditional type 1 error. Okay. Now, I've historically said this historically been associated with the selection of a chance example, and then I asterisk that. Why did I asterisk that? This gets into why we can't interpret null hypothesis or sort of our p-values as the likelihood of obtaining a sample by chance. If we were following all of our supplemental assumptions, then yeah, we could say, yeah, just at random we got that, but we're never doing that, right? So we can't interpret null effects or p-values as the probability of obtaining a sample of this size or this extreme or more
by chance, because it's not by chance, because we're always violating something wrong with assumptions. It's not just about the null, it's about representativeness, random sampling, all of our assumptions and things along those lines. So classically, in theory, yes, by chance, but we can also get stuff that falls way out here because we don't have good samples, we have imperfect measures, all these types of things. Alpha set by error investigator to determine threshold, 0.05, 0.02, right? And again, assuming probability of taking data, assuming no hypotheses and all observable hypotheses is the important thing here. Threshold for our type 1 error, 0.05 is 1.96, 0.01, 2.58, 0.001, 3.29. These are all based on your Z tables. These will be standard all the time for any Z tests that you run. Our type 2 error, this is when we fail to reject the null hypothesis, when the null hypothesis is really false. This is probably a much bigger issue in our science. Theoretically, we'll be in the next lecture. This is always the error that we make when we fail to reject, most commonly associated with insufficient power. All right, we'll finish up just that last piece next week to start off and finish off this lecture series. So, okay, any questions about what we've covered up to this point? So, we know we got problems at 2, due Friday at noon. Same thing. You all did a fantastic job of snapping photos of your homeworks in terms of your handwork and things like that. Only thing, sort of, when you plop that in there, make sure it's not so itty bitty that CJ and I can't actually see what you've done, because that's not helpful. And sort of, if there's been a mistake, to make sure that we've gone through and corrected it. But fantastic job getting stuff to CJ, getting stuff to me. Yeah, same deal. If you have any questions, let us know. But you all are off to the races. So nice work. Cool. All right. Thanks, folks.